Right. What marks the discussion today, and what marks in particular the beginning or the inception of our discussion, is the most popular section in this module, the Pade rational approximation. So we use these rational functions to perform the approximations, and today is not at all a very different day, but we are focusing on what really underpins these Pade rational approximation technique. But we suppose that R is a rational function of degree n plus m. So it's key to realize that R itself becomes a rational function. What is the degree of the rational function R? Is the sum of the degrees of the parts in the numerator and the denominator. So it becomes a sum of the degrees of the polynomials that feature in the numerator and the denominator respectively. Right, and obviously R becomes a rational function of the form that we shall see how this question is asked in assessments. But now we look at the fact that if R is a rational function of this form that is used to approximate a function f, we use this rational function to approximate a function f on a closed interval I containing 0. On a closed interval I containing 0. For R to be defined at 0 requires that. So for R to be defined at 0 requires that this constant be non-zero. So in other words, we have a tendency to say, we understand that the interval is actually contains 0, and we are approximating the function f on a closed interval I that contains 0. So because the interval contains 0, if ever we are to make every x equal to 0 here in the denominator, all these terms will become 0, leaving us with q naught. To avoid division by 0, we actually require that q naught at least be not 0 alone, so that even if these become 0, then we do not have the case of division by 0. Next. In particular, so in fact, we focus on the most underpinning aspects of this. In fact, we assume that Q naught is 1. I must indicate that we always do in this module, assume that Q naught is 1. For if this is not the case, we simply replace P of x, and we can see that P of x is what appears in the numerator and Q of x appears in the denominator. So if it's not the case, if we assume that, in fact, we assume that this is Q naught is 1. For if this is not the case, we simply replace P of x by P of x over Q naught, and Q of x by, obviously, in the denominator by Q of x over Q naught. Consequently, there are actually n plus 1 parameters, which are namely Q1, Q2, up to Qm, P naught, P1, up to Pn, available for the approximation of f by R. Okay, we shall understand what this means. So as a consequence, you'd have therefore n plus 1 parameters. And these parameters, which are Q1 up to Qm and P naught up to Pn. Okay, so you actually note that it's Q1 up to Qm and P naught up to Pn available for the approximation of f by R. Okay, so obviously, I mean, why do we have P naught up to Pn? It's simply because you have P naught up to Pn. Those are the parameters. And obviously, we're looking at the case where we're assuming that this Q naught is not 0. If it's the case that this one, if it is the case that it is 0, then we use the other parameters to approximate. So the parameters we therefore consider, we'll consider then from Q1. Why do we therefore consider from Q1? Before, if this is not the case, if it is not the case that Q naught is 1. And we use these parameters as those that are available for the approximation of f by R, and we continue with ease. Next question. Okay, so we look at an example here that can be used with ease. Right, here is a very, very interesting example. Right, the first example focuses on the use of the Pade approximation. We begin as follows, and we say the Maclaurin the Maclaurin series expansion for e to the minus x is is I to naught minus 1 to the power I divided by I factorial x to the I. The Maclaurin series expansion for e to the power minus x is this one here. And the question then becomes, you need to find the Pade approximation to e to the power minus x of degree 5 with n equals 3 and m equals 2. So it is of degree 5, but now the question is clear on the fact that the n equals 3 and the m equals 2. So the n is in the numerator, is the degree of the polynomial in the numerator, and the m is the polynomial, or is the rather the degree of the polynomial in the denominator. So, and obviously, numerator is therefore of degree 3 and denominator of degree 2, and therefore we sum the two to find the degree of the rational function r. And now we need to find the Pade approximation to e to the minus x of degree 5, given this particular Maclaurin series expansion for e to the power minus x. The question is, how do we solve this problem? We proceed as follows. Solution. Right, to look at the solution to this, we need to reason, but very carefully, and note that in particular to find the Pade approximation, we need to choose P naught, P1, P2, P3, Q1, and Q2 as well, so that the coefficients, so that the coefficients of x to the power k For k is not 1 up to 5 are 0 in the expression. Okay, we note this statement to actually say effectively to find the Pade approximation, we need to choose P0, P1, P2, P3, Q1, and Q2, so that the coefficients of x to the power k for k equals 0 to 5 are 0 in the expression. Okay, we're going to see and understand what this actually means. Like we saw before, because the numerator is of degree 3. And according to this, we take obviously P0 to Pn, n being the actual degree of the numerator, and the Q, now the Q's we take from Q1 up to Qm, because m is the degree of the denominator. So we continue to solve this problem, but we solve this problem in detail. So we continue. We continue. Right, so to continue now to solve this problem, we reason as follows. Okay, there's an expression, and the expression is the following. It is the 1 minus x plus x squared out of 2 minus x cubed out of 6 into 1 plus q1x q2x squared. Okay, we actually have said that for the q, we just take q0 to be 1. And that is what we have done here. Because we are looking at the q, and q is what appears in the denominator. And this here is the e to the power minus x. Is its Maclaurin expansion given in the question. And we then analyze this and say, what is then the meaning of this here, and what do we then do with this here? So we then from this, look at this carefully and then subtract from it. Right, so we then subtract from this what? Okay, so we continue. We continue. Okay, we continue. Now, the couple of things I want us to obviously analyze here is we look at these. And as we think of these very, very carefully. Right, we equate these to, in particular, we equate it to P0 plus P1 plus P2 plus P3. Like this. Okay, this is exactly the same as these. It's exactly the same as this. If you cross multiply this, it will be R. And then we multiply that by the denominator by cross multiplication, and it equals the numerator. So it's okay. We have this. we have this expanding. Right, so we proceed to expand and we collect like terms together. And collecting terms produces okay, so obviously we proceed to collect, so collecting. Expanding and collecting terms produces what? Right, so obviously if we expand these things and we compare the terms, so what do we achieve out of this here? So there's x to the fifth power. X to the fifth power is going to rise if you multiply this with that. We're just expanding this. Multiply this x cubed by this is going to produce x to the fifth power. But there's going to be a fifth power polynomial on the left, but there's no fifth degree on the right. So it actually obviously has a couple of implications for us to then consider. So it therefore means, therefore, that if you multiply for the fifth power, you're going to have minus 1 over 120. 1 out of 24. Q1. 1 out of 6. Q2. The coefficient of x to the power 5 is going to become 0 on the right of this because there's no x to the fifth power. Expanding and collecting terms produces this. Now, x to the fourth power. Okay, there's going to be an x to the fourth power, which is going to arise when you multiply these with that. Okay, these are factorials, please. You see? Well, they're not factorials. Okay, because 3 factorial is already 6. Okay, but 2 factorial is already 2, so yeah, it's okay like that. Now, but there's going to be an x to the fourth power that's going to arise when you multiply these with that. And so the x to the fourth power is going to arise when you multiply these with that. But not only this with that, the x to the fourth power, because even when you multiply x cubed with this one, there's going to be x to the fourth power. So the x to the fourth power are going to be many. Like we're going to analyzing these. These are also x to the fifth power are going to be many because these powers keep going up. They keep going up. X, for example, to look at this with a careful eye, you can be able to see that this one with these is going to be minus Q2 over 6, which is going to be x to the fifth power. That's x to the fifth power. Then there's going to be, for example, another x to the fifth power that's going to arise from multiplying this one with the x to the fourth here. These alternate, but x to the fourth is going to be x to the fourth over 24. So it's going to be this with that. But x to the fifth power is also going to arise if you multiply this one with the x to the fifth power because it's cubed here. This goes on. And then you're going to have the minus 120. But also, x to the fourth power is going to arise how? Okay, so that one is going to be 1 out of 24 minus 1 out of 6 Q1 plus 1/2 Q2. And this is naught. In other words, there's going to be x to the fourth power that's going to rise. But how will x to the fourth power rise? For example, this one with this one is going to produce Q2 over 2. X to the fourth power is also going to rise if you multiply this with that, because x cubed by x to the fourth power, which means it's minus Q1 over 6. But there's going to be another x to the fourth power that's going to rise, because here this one is x cubed over 3 factorial, which is 6. And then there's going to be plus x to the fourth power over 4 factorial, which is 24. So it's 1 out of 24. X to the fourth power is going to rise like that. So we continue. And then we look at x to the fourth, x to the fifth power, x to the fourth power, and then look at x cubed. X cubed is going to arise from the fact that if you, what combinations are going to, okay, so you just multiply this is that. Okay, it's easy to look at it from this side because it's more finite, but this one has like an infinite number of the terms. So it's tricky to look at it, but it's easier this way. So we're looking for what? We're looking for x cubed. So x cubed is going to rise if you multiply 1 with minus x cubed over 6. So it's going to be, there's going to be a minus 1 over 6. There's going to be a minus 1 out of 6. Okay, that's going to give us an x cubed, but also x cubed is going to rise when you multiply q1 with this one, with the x squared over 2. So there's going to be a q1 out of 2. That's going to be plus q1 out of 2. Then there's going to be another cube that's going to rise from the multiplication of this square with the minus x, which is going to be an x cubed. And that's going to produce a minus q2. But this one is going to be equal to the cube on the right, the coefficient of x cubed, which is the first one on the right, because the highest degree is 3 on the right. So we're going to have P3 there. We have P3 there. And then we have x squared. So we continue. We continue. We continue. Next point. Right, there are more things that we need to continue to sort of begin to analyze about this. Okay, we're looking at the quadratic x squared. X squared is going to rise if you multiply first this one with this one. So there's going to be just a 1/2. Okay, we're only taking the coefficients because even here we're going to take just P2. So multiply this with that. There's going to be x squared over 2, but just take only the coefficient. So 1/2. And then obviously another x squared, we're done with the 1. This one is going to rise and multiply this and this with this. So it's going to be a minus q1. Minus q1. And then that's x squared. Okay. Okay, we dealt with the x squared that's going to arise from the x, and then there's another x squared that's going to arise from the multiplication of this one with 1. So that one is going to be only a q2, taking only the coefficient. Q2 x squared by 1 is going to be only a q2. Right, so this q2 is going to be equal to the quadratic on the right, which is p2. And then there's going to be the linear one, x. For x is going to be 1 times minus x. So it's going to be minus 1 coefficient. Right. We continue. Okay, we have minus 1, and then also for the x, how else can you get x if multiply? It's we said that it is 1 by minus x, but it's also q1x by 1. So this is a q1. Did I write the q1? Did not. So we continue. We continue now. We look at more things that matter. Right. Okay. But now, what is the coefficient of x? Is p1 on the right. Now there is so we can find the Pade approximation that we want of a given polynomial f. So we continue. Now there is x to the 0th power. X to the 0th power. So we continue. All right. X to the 0th power, the constants. So it's 1 by 1, which is 1. Then there's no other constant that's going to arise. So it's just 1, the number 1, and then must be equal to p naught. Like so. Solving the system gives P1 equals. So in other words, right now, we need to solve for the system. It gives a P naught. What is P naught? Is 1. Take P naught to be 1. P2. Well, first P1. Here I mean P naught is 1. Because you can see that P naught is 1. All right, so if P naught is 1, then we want to find P1. So we can be able to get some of the things here like Q1, Q2. This is just simultaneous equations into unknowns. And then once you get the Q1, Q2, just plug them into these. Right, and then now it's easy to do that. But that's going to produce P1 because that's P naught. So we continue. We continue. We continue. Right, so yeah, I was saying, okay, we can just, for reasons of evidence, just simplify these things. Right, looking at these two equations, so what would the values of the Q1 and Q2 become of this? Right, so I'll take just a split second to quickly do this. It's not difficult. Just give me a split second. I'll have to capture this on my system. Just about 1 minute. We're gonna solve this one now. So we want to solve this, and we solve it by using an algorithm on my program I'm using here, called the substitution algorithm. So what you have here is that you have minus 1 out of 120 plus 1 out of 24 1 out of 24 Q1, and then there is the minus 1 over 6 Q2. Okay, I'm trying to just make sure that you just get some accurate answers so that everything becomes evident. Right, so there is 1 out of 6. Right, I'm trying to get the values of Q1 and Q2 quickly. And then you have that the result of this equals naught. Right, and then you have on the other side 1 out of 24. So you'd have that 1 out of 6. And then you would have 1 out of 12. 1 out of 2, excuse. Okay, equals naught. Right, so my program gives me, and you can do this, is just like 2 variables, so it's a problem in 2 unknowns. So what my program is able to give here is that Q1 is actually 2 out of 5, and Q2 is 1 out of 20. Okay, obviously we'll test this. Right, so getting those as the solutions to this into unknowns very difficult. You can even form a matrix and solve that, but it's not really quite of interest here. So now it would mean a couple of things. Like at this point, what is the implication? So it's going to be minus 1 plus Q1. What is Q1? Which is 2 out of 5. Which is minus 5 plus 2, which is minus 3 out of 5. Yes. So this one here, P1 becomes minus 3 out of 5. The next thing we're going to find is P2. So here we put just Q1 and Q2. Let me use the yellowish color. So you'd have the figure this implies. 1/2 minus Q1. We found Q1 to be minus 2/5. Q2, you found it to be 1/20. And that means that P2 equals. So, okay. We just have some nice little basic fractions. So if you have 1/2, 1/2 minus 2/5 plus 1/20th. It is 3/20. P2 is 3/20. This is the correct answer. P2 is 3/20. That's P2. Then now we're going to focus on P3. Right, so P3 is going to become what? Okay, we can get it out of this. So taking these down, what are we able to get? So, which means now we have this one here. What is Q1? Is 1/2. Okay, so we find first Q1. Okay, we got that one, which is 2/5. Q2. 1/20th. Okay, let's just simplify this and get exactly what the result is. Now let us 1/6 plus 1/2, yes, into Q1, which is 2/5 minus 1/20th, which is so that means P3 is minus 1/60th. Right, so able to see that this one is minus 1/60th. All right, okay, just doing the Pade approximation here. We shall do some exam questions today. Right, and then now with this, what is next? Okay, we found all the P's because it's P0 to P3, and then we just need to find the Q's also. Just need to remember the Q's were just Q1 and Q2. We've already got. Q1 is 2/5 and Q2 is 1/20. These are the correct answers. So these are also there in my textbook, in the prescribed textbook. I've taken this exercise from the textbook. So it has already been done with a couple of typing errors in the textbook, but by and large, this corresponds to what they got as well. Okay, so show that we are pretty happy with this. Now what we then do, and with these then we're able to then say so the Pade approximation is out of X. Okay, so we need to think of the fact that the Pade approximation is the expression that is the p's. So it becomes the p0, p1x, p2x squared, and so on to p3x cubed, and then the q's will be this one here, which is the p naught plus p1x plus p2x squared plus p3x cubed. So this one is squared. And then this is 1 plus q1x plus q2x squared, which means, therefore, we perform substitution. What is p naught? We have seen that p naught is 1 and minus 3 over 5 and so on. P naught is 1, and then P1 is what? Is minus 3 over 5. Minus 3 divided by 5. X P2 plus 3 out of 20. P3 minus 1 out of 60. X cubed. 1 plus Q1. We got 2 out of 5. X for Q1 and Q2, we got it to be 1 out of 20. X squared. Okay, this is just one example on how to study the Pade approximation, but let us look at a little bit more examples so that we can try to make a bit more sense of these in the context of more problems. And the, what you call the Chebyshev polynomial approximations, but it will be very helpful to look at an exam question on these, as there was an exam question this past November. Here's an example. Here's an example. Okay, so we are given the truncated power series. Given the truncated power series. One minus x plus x squared out of 2 minus x cubed out of 3. It's another example, this one. Plus x to the 4th power out of 4 minus x to the 5th power out of 5. Okay, so we have this. right? Given the truncated power series, which is this, when it's a power series, the power series ordinarily are infinite, have an infinite number of summands or terms. Now, this one is truncated in the sense of it's terminated. Next, in the, oops, I want to do white. In the Chebyshev polynomial. Okay, the Chebyshev polynomial T5. Which is 16 x to the 5th power minus 20 x cubed plus 5x Here comes the first question. Number 1. What is the purpose of economizing a power series? We look at the solution to this. Given the truncated power series this and the Chebyshev polynomial that, what is the purpose of economizing a power series? Here's the answer. The reason is that an economized can use American Z. British would use S for that. An economized power series gives almost the same accuracy as the original one. With fewer terms. An economized power series gives almost the same accuracy as the original one with fewer terms. So if you economize it, you're dealing with fewer terms, but you have the same accuracy, and that is the advantage of economizing a power series. Fewer terms, easy to manipulate than lots of terms, but with the same accuracy. How awesome is that? All right, it is so awesome. All right, so now that is the point. But here comes the next question. Here comes the next question. economize the power series P of X. Economize the power series P of X. So you continue. How do we economize this power series? We see how to do that. So instead of really saying find the Pade approximation, they are really saying economize it. So we continue to do that. Right, to economize the power series P of X, we look for the solution to that and we look at part 2. We know that obviously we agree that P of X is given. It is as given. 1 minus x and so on, up to minus x to the 5th power. One minus x plus x squared out of 2 minus x squared out of 3 plus x to the 4th power of 4 minus x to the 5th power of 5. Let's economize P. And here is the power series P of X. Truncated version, that is not up to infinity, an infinite number of terms. Right, to economize it, we need to be very, very careful, but also perform some algebraic manipulations. We take the P power series that we need to economize and take the Chebyshev polynomial and analyze the degrees of this. In other words, what is the degree, for example? So now we need to remove the highest degree of these. The highest degree is x to the 5th power. So we need to remove x to the 5th power. Now let us check. This one has also x to the 5th power. So it's 16 which means it is t which is 16x to the 5th power plus 5x. Okay, that is the t, the t5, which is the Chebyshev polynomial of degree 5. Right, so we need to eliminate the 5th power. So let's eliminate the 5th power by any algebraic manipulation possible. So to do this now, we have that this one here is exactly P of X we have, and then we need to subtract something. We need to subtract these, but we need to put a coefficient here that is going to allow us to remove this, to remove x to the 5th power. So how? So it actually means that we want the coefficients to be the same. So we can multiply these by the following. If you multiply this one by 5. Okay, you can multiply it by 1 over 5 and then remove the 16. Multiply it by 1 over 5 and then remove the 16. Multiply it by 1 over 5. So T5. Right, so we have these. So we multiply this one by the 1 over 5 like that. So what does it become? The P of x is 1 minus x, and then you have x squared out of 2, and then we have x cubed out of 3, and then that is P of x. And then you have x to the 4th power out of 4, and then x to the 5th power out of 5. So you multiply these by that. So the 16 is going to cancel out, giving us, so we need to add. We need to add, because if we minus, it's going to be minus this, minus that, and it's not going to help. So we need to add. Right, so if we add, then algebraically, we multiply this one by this, or multiplying, so the 16 is going to cancel out, giving us 1/5 x to the 5th power, which is going to work. It's going to work wonders. And then now you multiply this one by that, so you multiply by this, it will be 20 out of 80. Because 5 by 16 is 80. So it becomes a 4. But obviously you're adding with this, so it's going to be exactly a minus x cubed out of 4. And then if you multiply this with that, then you have plus x to the 16th x out of 16 there. Okay, so we continue right now to analyze this Pade approximation with a specific focus on P of x plus P of x plus 1 out of 5 by 16 times the Chebyshev polynomial of the 5th degree. What is happening here? Okay, x to the 5th power is going to disappear. Good news, because the aim of economizing a power series is to remove the highest degree, but then we have fewer terms. Okay, then how many constants are there? There's only this one. So we're just going to carry that forward. Next, we have the linear terms. Okay, so this one and these are linear. So what is minus x plus x out of 16? So it is minus 16x plus x, which is minus 15x out of 16. And then now, quadratic, degree 2 is going to be half x squared. There's only one. There's no other x squared. It's going to be 1/2 x squared. And then, okay, x cubed. There's going to be this one and this one. So minus 1/3 minus 1/4 is like minus 4 minus 3, which is minus 7 out of 12 x cubed. Minus 7 out of 12 x cubed. Okay, that's the x cubed. What about x to the fourth power? And this is it. This is it. So hence, the implication is therefore that P of x plus 1 out of 5 by 16, T5 of x is 1 minus 15 plus x squared minus 7 out of 12 x cubed, x to the fourth out of 4. And this is the answer. Okay, we have economized this power series. How did you economize it? We removed the highest degree by using the Chebyshev polynomial of degree 5. Next question. Next question. What is the maximum? What is the maximum value of t sub 5x in the interval what is the maximum value of the modulus of t sub 5 of x solution? So given right, so here we're given t sub 5x, which is 16x to the fifth power minus 20 x cubed plus 5x. So we get the modulus of this. What is the maximum value of these? So we're interested in the maximum value of the modulus of t sub 5 of x. The maximum value is in the interval this. Okay, so what is the maximum value in this interval? So obviously, the couple of things that you need to analyze in an attempt to find the maximum value of the in this interval. So either way, for example, if you put the number 1 here, this becomes 16 minus 20, which is minus 4 plus 5. It gives us 1. What about if you put minus 1? It becomes minus 16 plus 20, which is a 4, plus 5, which is a 9. So either way, obviously, an analysis of these function demonstrates that the maximum value. I want us to analyze this very carefully. Okay, when you take x to be 1, what do you get? You have 16 minus 20, which is minus 4 plus 5. It gives us a 1. What about minus 1? So you'd have a minus 16 plus 20, which is exactly 4, minus 5, which is a minus 1. So anyhow, the maximum will, it is indeed 1. There are a couple of ways to demonstrate that, even by the use of calculus, to analyze all possible extrema of this curve. But obviously, normally it's not intended to be a very difficult question. It can be even done using metric understanding of calculus in terms of finding the local extrema, be it the global minimum, the global max, etc. But yeah, in this case, the maximum will be 1. The maximum is understood in this case mostly to be located in the, because this interval is closed. It is a closed interval. Because it's closed, then the maximum is by and large often occurs at the endpoints of this closed interval. Okay, it's closed because of the parenthesis, square parenthesis. Okay, next question. Right. If Q of X denotes, if it denotes the economized okay, can use the American Z in this question. The American Z for the word economized. If Q of X denotes the economized series, obtained in 2 above, what is the maximum? What is the maximum value of Q of X minus Q of X? In the interval. If Q of X denotes the economized series obtained in 2, we've seen it, what is the maximum value of the difference in the interval? Right, so we look at the solution to this. So what becomes the solution to this? Now, the couple of things remain very important. Okay, Q of X is the economized one. So we called it this, P of X minus 1/5, 1/16 minus 1/5 16th T5 of X, which is P of X minus 1 of 80. So what is this? Q of X is P of X. Which means Q of X is P of X minus 1 out of 80 which means therefore that the P of X minus Q of X. Okay, Q of X is the economized one. Okay, 5 by 16 is 18 in the denominator, so that P minus Q therefore becomes 1 out of 80 into the modulus So now you have this. We have seen that the modulus of the T5 is the maximum of the T5 is 1. 1 out of 80. So that P of X minus Q of X is less or equal to 1 out of 80, which is 0.0125 when minus 1 is less or equal to X, less or equal to 1. So we're able to see the fact that this economized power series itself is or rather the modulus of P minus Q, P of X minus Q of X is has the maximum of 1 out of 80 when X lies between minus 1 and 1. When X lies between minus 1 and 1. And we continue. So next. Next question. Right, so that was part A of the question. Now we look at part B of the question. In part B of the question, what do we want to do? We want to find a Pade approximation. R6 of x with denominator of degree 3 to the function and then you have x to the 4th power out of 2. Right, we want to find a Pade approximation of degree 6. Okay. With the denominator of degree 3. So the denominator is of degree 3, it means the numerator is going to be of degree 3, because if you add the degrees of the numerator and denominator, you get the degree of the rational function. Roman figure 1. Why? Why is it often preferred to approximate a function by a rational function rather than by a polynomial. Why is it often preferred to approximate a function by a rational function rather than by a polynomial? Question mark. Next. Next point. Roman figure 2. Write down R6 of X with the coefficients. With coefficients AI and BI. Roman figure 3. You need to set up the equations. Need to set up the equations to find the coefficients. But not do not solve the system. But do not solve the system. Solution. Right, in our quest to sort of understand Pade approximation, we proceed as follows. We proceed as follows. We proceed as follows. All right. We want to find a what we call a Pade approximation here, R6 of X. With the denominator of degree 3 to the function this. Why is it often preferred to approximate a function by rational function rather than a polynomial? Why rational? Why not just instead of a rational function, just using a polynomial? Why? Solution to this. That is part B, first Roman figure, a rational approximation. A rational approximation can give greater accuracy for the same number of coefficients. Or the same accuracy with fewer coefficients. With fewer coefficients. A rational approximation can give greater accuracy for the same number of coefficients or the same accuracy with fewer coefficients. So this rational function or a rational approximation can give greater accuracy for the same number of coefficients or the same accuracy with fewer coefficients. Yes, same number of coefficients, greater accuracy with the same number of coefficients, or potentially fewer coefficients, because you can see that like these are 6. So if the denominator is of degree 3, then the numerator becomes of degree 3, then so you can have the same number of coefficients or potentially even fewer coefficients anyway. So that is the advantage of this rational approximation versus versus the rest of this, versus the polynomial, versus the polynomial. Right. Okay, we continue. Now, what do we do with this? Okay, we're just explaining the first part. Why is it often preferred to approximate a function by rational function rather than a polynomial? We have elaborated on that one. And write down R6 of X with coefficients AI and BI. So we need to just write a general thing. So don't stress with the fact that this has to be the actual Pade approximation, but it should not be the accurate one, but with coefficients AI and BI. So we good. Just write something general. But obviously writing the general thing with the understanding that the denominator is of degree 3. So the denominator is of third degree in B2. The denominator is of third degree in B2, so that R6 of X can be seen as, we always put a 1 here, so that denominator is never 0. And then we'd have A0, A1X, A2X squared, plus A3X cubed, B1X, B2X squared, B3X cubed. So this is R6 of X. This is R6 of X. So we good. We have AIs and the BIs. So we always start from the top. So the A's are in the numerator and the B's, like you say PQ. So we have P as the numerator and Q as the denominator in the definition we wrote earlier. So in other words, we then say R6 let me write at the bottom here. R6 with denominator with denominator of degree 3 is of degree is okay. R6 with denominator of degree 3 is is shown here with above. Here with above, like this. Look, there are a couple of things that we need to consider here. You look at a new question. Right, look at the new question, like our next focus question. Third Roman figure, B, third Roman figure. Write down R6 of X with coefficients AI and BI. Set up the equations. Set up the equations to find right. You need to set up the equations to find the coefficients, but do not solve the system. So we need to find the coefficients. Right, let's find the coefficients like we found before in the first example I gave. But do not solve. Okay, with time we can see if we can solve, but we don't have to solve. Okay, now to set up the equations to these, we proceed as follows. Right, first things first, we need to understand that you have the AIs at the top and then the BIs at the bottom. Okay. So with that said, what do we then do here? Because if you look at this question, they're saying we want to find a Pade approximation R6 with denominator of degree 3 to the function this. So we have been given this function, EX squared. So we're looking at B third Roman figure. So we given e to the x squared. E to the x squared, which is R6 of x. Like so. Which is R6 of x. Or what we'd rather do is to subtract. Because if we want to find the Pade approximation to the x cubed, we can just subtract the R6. Like so. And if we subtract that, what is the E? What is the E? E to the x squared is 1 plus x squared. This one is 1 plus x squared. Plus x to the 4th power over 2. Plus x to the 6th power out of 6. And so on. Minus, what is R6? It is A naught, A1x, A2x squared, A3x cubed. And then you remember here, always put a 1. But degree 3, so is b1x, b2x squared. Degree 3, b3 x cubed. Right, we have this. So what do we do with these? What we do with these is we add these things. So this one being the LCD, so you can take this one to become the LCD, and we then multiply this one by that minus this. So to sort of cross multiply it, to take the LCD, doesn't matter how one looks at it. So we take the LCD to be 1 plus b1x plus b2 x squared plus b3 x cubed. And then we multiply this with that. 1 plus x squared x to the 4th out of 2 and then x to the 6th out of 6. So we continue. We continue. Right, so what next do we do now? Okay, we continue, please. So we continue. All right, we continue, please. Just a sec. Right, so if you take the LCD of these, this is out of 1, so you'd have that it would be this into this 1 plus b1x. So plus b2x squared plus b3x cubed minus a naught a1x a2x squared a3. So now, if you look at these carefully, we want to find set up the equations to find the coefficients, but to not solve the system. What we want to do, in a series of steps, we want to find the Pade approximation R6 of x with the denominator of degree 3 to the function this, with denominator of degree 3 to the function this. But we go through some steps. And the strategy to find a Pade approximation R6 of x with denominator of degree 3 to this function is to subtract the 2 and say this one goes up to infinity. This rational function is therefore subtracted from this here. Okay, so it's e to the x squared minus R6 of x, like this. And then we are able to proceed from here. But what do we achieve from this? In the numerator, B third Roman figure, in the numerator, set the coefficients of terms one x up to x to the 6 equal to 0. Right. So in the numerator, set the coefficients of terms 1x, x squared up to x to the power 6 equal to 0 in the numerator. So we'd have, therefore, the coefficients of the constant x to the 0. If you look at the coefficient of x to the naught, what does this become? What does this become? In the numerator, so you'd have 1, 1. And then you'd have minus a naught. And that is going to be which is 1 minus a naught, which is equal to 0. You set them equal to 0. Now, this is a very good trick because we really are subtracting these such that we are trying to sort of equate this, and we're trying to make sure that these are sort of equal to each other. And yes, please. All right, yeah, I'm in class. Just give me like 5 minutes. All right. So you have the constant, which is 1 minus a naught. And then now let's look at the next, like the x. Okay, there's going to be an x here. Any other x that's going to come. So the x is going to come from b1 by 1, for example. And that's going to be b1 x in the a1. So it's going to be b1 minus. Yeah, so this is going to be an x. b1 minus a1. x2. Let's look at the x squared. So x squared is going to come from what? It can come from many things, but if you multiply, for example, b2 with 1, and also you multiply b1x with, okay, b1x is not going to produce that, but the b2 with 1, and also the 1 with the x squared. So those ones are going to produce x squared. So which means that you're going to have the b2 and also the 1. And then also there's going to be minus a2 x squared. So which means for the x squared, you're going to have b2 plus 1 minus a2 equals 0. X cubed. By x cubed, let's look at the x cubed terms. So you're going to have like b1 x squared, b1x and x squared, which is going to bring a cube. And then a couple of cubes are going to appear from this, like your yeah, that's the b1 and x squared. What else? The b3 x cubed by 1, and there's going to be minus a3. Yeah, so that's going to be b3 plus B1 minus A3 equals 0. Then you have x to the fourth power x to the fourth power. X to the fourth power is going to come from 1 by the x to the fourth power out of 2. So it's going to be 1/2. But there's going to be, okay, there's no x to the fourth power here. But another x to the fourth power is going to come from B2 x squared by x squared, which means x to the fourth power is going to yield B2 plus 1/2 equals 0. X to the fifth power. X to the fifth power. So x to the fifth power is going to appear in many ways. Like you can take this one, x to the fourth power, multiply with B1. It's going to be x to the fifth power. Another x to the fifth power is going to be B3 and x squared. With x cubed, it's going to produce x to the fifth power. So x to the fifth power is going to have the following coefficients. What are you interested in the coefficients? So we're equating everything to 0. Very, very clever trick in this question. Presenting a different dimension to the Pade approximation technique. So this one is B3 plus half B1 equals 0. Like this. Like this. Okay? Then let's look at x to the sixth power. Right, x to the sixth power is going to produce what, for example? Let's check. X to the sixth power is going to be this one, 1 by this, which is x to the sixth power. But another x to the sixth power is going to come from B2, because if you say B2x squared by x to the fourth is 1/2 x to the sixth power. Plus 1/6 equals 0. Like this. So it's half B2. Okay, obviously the question asked us not to find the coefficients because they said do not solve these, but we can proceed to solve these. I've just looked at them and I realized that it's just very, very easy to solve them. Right, because here's the question. Because we're just practicing with this, write down the R6, set up the equations. Yeah, set up the equations to find the coefficients, but do not solve the system. Do not solve the system. But this one is a very, very simple system to solve. Like, if you look at it very carefully, I'm going to do it in the orange color or yellowish color. Like, it's easy to find A naught. It's 1. Okay, B1 is A1, not very useful. Not very useful here. B1 is A1. Here you can be able to find that B2, for example, equals minus 1/2. And here you can be able to find B2 okay, it's a very sort of funny thing because it's resulting to a problem here, because if you look at B2 equals minus 1/6, and B2 then if you cross multiply is going to be minus 1/3. So it's going to be minus 1/3, but B2 here is going to, it's just minus 1/2. Okay. Interesting, but it's not consistent. So it's just sort of inconsistent. Okay, because for B2, you're getting two different values. Right. So a very inconsistent system. But anyhow, we have solved this question to this extent, meaning that it is sort of inconsistent. You'll have a wide range of the values, etc., a wide range of the combinations of these values. You can get, yes, please. Okay, yeah. Okay, that's fine. Yeah, okay, please give me a couple of minutes. I will get back to you. Yeah. All right. So as a consequence, then we have that. But it is certainly the Pade approximation, but he said we did not have to solve this. And we have discussed the Pade approximation today. It is by and large the sort of the greatest extent to which it can really go in depth. Right. So we should continue our discussion tomorrow, looking at more things, this module, more exams, more exam questions, more past exams. So that is the objective as part of my tomorrow strategy, to cover more past questions. So yeah, we shall meet then tomorrow at 4 p.m. I'm believing that that is fair enough this time. It's fair enough. Okay, because it allows somebody to wake up and do a couple of other things before the discussion, something like that. Okay, right. I'm going to upload the video in the next couple of minutes. So thanks for today and see you tomorrow at 4 p.m. and goodbye.
Hello.
Yes, please.
Can we start going over exam papers?
Yes, tomorrow. Tomorrow. So tomorrow we shall go through a wide range of, I'm going to upload a lot of them.